Dear students, Namaste and welcome back to a new mathematics session. In the previous session, we have discussed problems from exercise 11.2. Hope you have revised well. In today's session, we shall discuss the basic concepts of plane and the equation of plane under different circumstances. Let's move on to the topic. Before starting the session, let's recall the formulae of lines in a plane. The first one is point parallel form. Vector equation is vector r is equal to vector a plus lambda into vector b, and the Cartesian equation is x minus x1 by a equal to y minus y1 by b equal to z minus z1 by c. Here a, b, c are the direction ratios. Instead of direction ratios, if direction cosines are given, means a, b, c can be replaced by l, m and n. Next, 2-point form. Line passing through 2 points whose position vectors are a and b. Vector form is vector r is equal to vector a plus lambda into vector b minus vector a. And the Cartesian form, when x1, y1, z1 and x2, y2, z2 are the 2 points coordinates are given to you, means the formula is x minus x1 by x2 minus x1 equal to y minus y1 by y2 minus y1 equal to z minus z1 by z2 minus z1. Next, condition for two lines to be parallel, that is vector b1 is equal to lambda into vector b2, or a1 by a2 equal to b1 by b2 is equal to c1 by c2. Their direction ratios are proportional, that is in Cartesian equation form. Next, condition for two lines to be perpendicular, that is vector equation are given to you, means vector b1 dot vector b2 must be equal 0. If the equations are in Cartesian form, the condition is a1 a2 plus b1 b2 plus c1 c2 is equal to 0. a1 a2 b1 b2 c1 c2 are the direction ratios. Instead of direction ratios, if direction cosines are given to you, means l1 l2 plus m1 m2 plus n1 n2 is equal to 0. Next, we learn about skew lines. Skew line means the lines which are neither parallel nor intersecting and they are lying in different planes, or non-coplanar. Shortest distance between two skew lines we have learned, that is there we have studied modulus together we have used, but here I'm just keeping separately because it is easy for you to calculate. Then both are same only. Modulus of b1 cross b2 dot a2 minus a1 divided by modulus of b1 cross b2, and the Cartesian form is determinant x2 minus x1 y2 minus y1 z2 minus z1 a1 b1 c1 a2 b2 c2 divided by root of b1 c2 minus b2 c1 the whole square plus c1 a2 minus c2 a1 the whole square plus a1 b2 minus a2 b1 the whole square. Next, we have learned about distance between, or the shortest distance between two parallel lines. There also we use the modulus together while studying, but here using separately, so it's not a problem, both are same. Which one is convenient, you can use it, that one. Here distance is modulus of b cross a2 minus a1 divided by modulus of b. So you have to by heart these formulas, and not only by hearting, you must be able to identify a1 b1 c1 a2 b2 c2. Then when equations are given to you like this form, that is r is equal to a plus lambda b, means vector a and vector b you must be able to identify. Then direction ratios and direction cosines, x1 x y1 z1 x2 y2 z2, all these things you must know how to identify from the equations. Now let's discuss the basic concepts of plane. A plane is a flat two-dimensional surface that extends infinitely far. In the picture, there is a portion of plane is shown, and by using this definition, we can say that this portion or this plane can be extended infinitely far. Means we can extend upwards and we can extend downwards, we can extend towards left and we can extend towards right. So a plane is a flat two-dimensional surface that extends infinitely far. A plane is named by 3 points in the plane that are not on the same line. If I consider 3 points A, B and C which are on this plane, provided these A, B, C are not in the same line, then we can use these 3 letters A, B and C for naming this plane. The plane shown in the figure can be named as plane ABC. Every plane is defined by its normal. We have already learned about normal. Normal in the sense a line or a vector which is perpendicular to the given plane. A line or a vector which is perpendicular to the given plane is called its normal. And if you consider this flat surface, or if you consider this plane, there are infinitely many vectors which are on this plane. This is one vector, this is another one, this is the third one, and this is the fourth one. So there are infinitely many vectors, and we must note that there is no relationship between these vectors which are on the plane other than being on the same plane. So, and if you consider a normal in the sense a vector or a line which is perpendicular to the plane, means angle between the plane and the line must be 90 degree, then we can call it as a normal. There is a relationship between this normal and the vector which is on the plane. There is a relation, and this relation we are using for finding out the equations of the plane, and this is the basic concepts for forming the equations of plane. I repeat, there is a relationship between the vector which is on the plane and the normal towards the plane. And the relation is the dot product of these two vectors, means the vector which is on the plane and the normal. The dot product of these two must be equal to 0 because they are perpendicular. The angle between these two is 0. So this is the basic concept. We must keep it in mind. All the lines on the plane will be perpendicular to a common line. We call it as normal. I have already explained this concept. And next is general equation of the plane. This you have already learned in class 11. The general equation of the plane is ax plus by plus cz plus d is equal to 0, where a, b and c are the direction ratios of normal to the plane. Normal to the plane means this one. Next, we shall discuss the equation of a plane. There are 5 equations we have to learn. The first one is normal form. If vector ON is the normal from the origin to the plane and n cap is the unit normal vector along ON. If you observe this diagram, vector ON is the normal from the origin to the plane. Vector ON, this is a normal. We have already explained about the normal. So normal means a line or a vector which is perpendicular to the given plane. So here ON is the normal vector and n cap is the unit vector along ON. N cap is the unit vector along ON. Means if you want to find out vector ON, we have to multiply this unit vector with its magnitude d. D in the sense the distance of this point n from the origin, that is d. So when you multiply the magnitude d with n cap, we will get vector ON. Let P be any point on the plane. I have taken one point P, coordinates x, y, z. These coordinates we are not going to use now. When we are deriving the Cartesian form, we will use this x, y, z. At present, we will take only the point P, and the position vector of P is vector r we have taken. So NP, vector NB is perpendicular to vector ON. As I have discussed before, NP is a vector which is on the plane and ON is a normal. So a plane or a vector which is on the plane and a normal towards the plane, both are perpendicular, means their dot product is 0. That is vector NB dot vector ON is equal to 0. So let's find out this vector ON first. Vector ON I have already discussed before. Unit vector along ON is given to you, that is n cap, and the distance is given d, or the magnitude is given d. So when you multiply the magnitude with the unit vector, we will get the vector ON. ON is equal to d into n cap. Then vector NP in the sense position vector of P minus position vector of N. Position vector of P we have marked here, that is vector R, minus position vector of N. Position vector of N in the sense ON. ON we have already calculated, that is D into N cap. So let's substitute it. That is vector NP dot vector ON is equal to 0. Vector NP we have calculated, that is vector R minus D into N cap dot vector ON. Vector ON is D into N cap is equal to 0. And here D must not be 0. A dot product is 0 in the sense either r minus d into n cap dot n cap means these are all vectors. This must be 0 or d must be 0. D, of course, it is not possible to get as 0 because d is the distance of that particular point n from the origin. So since d is a distance, d must not be equal to 0. That means vector r minus d into unit vector n dot n cap must be equal to 0. Then let's take the dot product, that is vector r dot n cap minus d into n cap dot n cap is equal to 0. That is r dot n minus d into n cap dot n cap, that is equal to 1. So this minus d, when it comes towards right, it becomes plus d. So r dot unit vector n is equal to d. This is the vector equation of the plane in normal form. And now we have to move on to calculate or finding out the Cartesian form. We can use these p, x, y, z coordinates. So let p, x, y, z be any point on the plane and L, M and N be the direction cosines of unit vector n. So once again, p, x, y, z be any point, arbitrary point on the plane, and L, M and N be the direction cosines of n cap. Then OP, that is, we can calculate OP, that is the position vector of P. Position vector of P we can write, since the coordinates are there, x, y and z. So xi plus yj plus zk, that is vector r is equal to xi plus yj plus zk, and n cap is equal to li plus mj plus nk. Since they are unit vectors, so we can use the direction cosines L, M and N. So n cap is equal to Li plus Mj plus Nk cap. Then when we substitute it, we will get R is xi plus yj plus zk. We are going to substitute it in vector equation. R dot n is equal to d. R dot n cap is equal to d. So vector R is xi plus yj plus zk dot, then n cap is Li plus Mj plus Nk is equal to d. That is, when we do the calculation, we will get it as Lx plus My plus Nz is equal to d. You know how to take the dot product, and I dot I and I dot j values we have to substitute, and we will get the final answer as Lx plus My plus Nz is equal to d. And this is the Cartesian equation of the plane in normal form. These proofs are not explained in the examination point of view, but if you know how to derive it, this one, it will be easy for you to solve the given questions in the examination. That is the purpose of explaining this derivation. Next, we have to note an important point for solving questions in the examination. If d is the distance from the origin and L, M and N are the direction cosines of the normal to the plane through the origin, then the foot of the perpendicular is LD, MD and ND. Foot of the perpendicular means the coordinates of the foot of the perpendicular can be calculated by using the formula LD, MD, ND. Here d is the distance from the origin. L, M and N are the direction cosines of the normal to the plane through the origin. If you visualize it, the foot of the perpendicular, this is the plane and the distance is given to you, that is d, and the foot of the perpendicular means the coordinates of the foot of the perpendicular means you have to find out the coordinates of this particular point. So this is called the foot of the perpendicular. So this is the visualization of that particular statement. Next, in the equation of plane, we will discuss point normal form. In the space, there can be many planes that are perpendicular to the given vector, but through a given point p, x1, y1, z1, only one such plane exists. The meaning of this statement is quite simple. There can be many planes that are perpendicular to the given vector. In the three-dimensional coordinate system, there can be many planes. If a perpendicular vector is given to you, there can be many planes which are perpendicular to the given vector. But a perpendicular vector and a particular point is given to you, means there will be only one such plane exists. Let's visualize this statement. The three-dimensional coordinate system x, y and z axis, and origin is here, and a perpendicular vector is marked, and through this perpendicular vector we can consider infinitely many planes. Here of course 3 are shown here, but if you extend this vector infinitely far, then we can include infinitely many planes which are perpendicular to the given vector. But if you consider a point on the plane, that is p x1 y1 z1, there will be only one plane which is perpendicular to the given vector and passing through that particular point. So we are going to form the equation of those planes which are perpendicular to a given vector and passing through a given point. So equation of a plane perpendicular to a given vector and passing through a given point. Let's observe this diagram. Here also derivation little bit I am explaining because it will be useful for you to solve the questions in the examination, but the derivations will not be asked. Here x-axis, y-axis and z-axis we have marked, and the origin is here, and there is a plane is mentioned, is shown here in the diagram, and there is a particular point in the plane, that is x1 y1 z1. A is the given point in the plane. The coordinates of A we have taken as x1, y1 and z1, and the position vector of A is vector A. And there is another vector is given to you, normal vector, that is vector n, which is perpendicular to the given plane. So these are the conditions, given conditions. A perpendicular vector is given to you and a passing through point is given. And the position vector of OA we have marked as A. As before, we will take another arbitrary point, that is p x y z, a general or a common point in the plane, that is p x y z. And in the beginning I have already explained to you a vector, that is AP, which is on the plane, will be perpendicular to the normal to the plane. Means vector AP and vector n are perpendicular, means their dot product is 0. That is a concept we are going to use, that is vector AP dot vector n is equal to 0. Vector AP, we know that position vector of P minus position vector of A. Position vector of P we have taken as vector R, and position vector of A we have taken as vector A. So vector R minus vector A. Let's substitute it. AP, the vector AP is vector R minus vector A dot vector n is equal to 0. Let's mark it as equation number 1, and this is the vector equation of point normal form. Now we have to find out the Cartesian form. For that, let the given point A be x1 y1 z1 and P be x y z. A is the given point x1 y1 z1 and P is the arbitrary point or a general point, and direction ratios of vector n are capital A, capital B and capital C, direction ratios. Let's substitute in equation number 1, that is equation number 1 in the sense vector R minus vector A, position vector of R minus position vector of A. Position vector of R in the sense here x and here it is x1. So x minus x1, that is the direction ratio. So x minus x1 into I cap plus y minus y1 into j cap plus z minus z1 into k cap dot. Here direction ratios are there, A, B and C, capital A, capital B and capital C. So vector n will be A into I cap plus B into j cap plus C into k cap is equal to 0. So when you pair it or when you solve it, we will get as A into x minus x1 plus B into y minus y1 plus C into z minus z1 is equal to 0. This is the Cartesian equation of the point normal form. Next, in the equation of plane, we will discuss equation of a plane passing through 3 non-collinear points. Let's observe the given diagram. There is a three-dimensional coordinate system, x, y and z axis are marked, and the meeting point of these three axes origin is also mentioned here. And there is a plane, and we have taken 3 non-collinear points, that is R, S and T. 3 non-collinear points we have considered, point R, S and T. The position vector of R we have taken as vector A, position vector of S is vector B, and position vector of T is vector C. And we have taken a fourth point, that is arbitrary point or a general point P. The position vector of P we have taken as vector R. Let R, S and T be the three non-collinear points on the plane with position vectors vector A, vector B and vector C respectively. Now little bit of explanation is needed here. If you consider vector Rs and vector Rt, the cross product of vector Rs and Rt will be a vector which is perpendicular to both vector Rs and vector Rt. By using the definition of cross product, we can say that when you take the cross product of two vectors, we will get a resultant vector which is perpendicular to both the given vectors. Once again, if you take the cross product of Rs and Rt, vector Rs and vector Rt, we will get a resultant vector which is perpendicular to both Rs and Rt. Now you know that Rs and Rt are on the plane, and if you get a perpendicular vector in the sense that vector will be perpendicular to Rs and Rt, in the sense that vector will be perpendicular to the plane itself. And we have got Rs cross Rt now as a single vector, and there is another vector here Rp, and this vector Rp and this cross product vector, that is vector Rs cross vector Rt, these two are perpendicular because now this vector Rs cross Rt is the normal vector and Rp is the vector which is on the plane. And the dot product of these two vectors, this Rp vector and Rs cross Rt vector, the dot product of these two vectors will be 0. So that is the concept behind this equation of a plane passing through three non-collinear points. So let's write it. Rp dot vector Rs cross vector Rt is equal to 0. Once again, first we have taken the cross product of Rs and Rt. So we have got a resultant vector, that is Rs cross Rt, which is perpendicular to both vector Rs and Rt in the sense which is perpendicular to the plane itself. Then we will consider this as single vector. Vector Rs cross vector Rt we will consider as a single vector, and Rp is another vector. So these two vectors are perpendicular. Because of that, their dot product must be 0. That is vector Rp dot vector Rs cross vector Rt is equal to 0. So once you substitute here, you will get that formula. That is vector Rp we can calculate position vector of P minus position vector of R. Position vector of P is vector R and the position vector of R is vector A. So R minus A dot Rs. Vector Rs we can calculate. Vector Rs in the sense position vector of S minus position vector of R. So position vector of S is B and position vector of R is A. So B minus A cross vector Rt means position vector of T minus position vector of R. Position vector of T we have got here vector C, and position vector of R. Position vector of R is vector A. So cross vector C minus vector A is equal to 0. So this is the vector equation of a plane passing through three non-collinear points. So instead of by hearting, if you know how to derive this formula, then it will be fine. Next we have to go for the Cartesian form. For that, let x1 y1 z1, x2 y2 z2 and x3 y3 z3 be the coordinates of the points R, S and T. R, S and T we have taken the coordinates x1 y1 z1, x2 y2 z2 and x3 y3 z3. Then we have taken an arbitrary point, that is P. The coordinate is x, y and z. X, y, z be the coordinates of any point P on the plane. That is a general point. Then the equation of the plane passing through three non-collinear points can be found by using this equation. Determinant x minus x1, y minus y1, z minus z1, x2 minus x1, y2 minus y1, z2 minus z1, x3 minus x1, y3 minus y1, z3 minus z1 is equal to 0. This is the Cartesian equation of a plane passing through three non-collinear points. Next, in the equation of plane, we will discuss intercept form of the equation of a plane. Let the plane ax plus by plus cz plus d is equal to 0 make intercepts a, b and c on x, y and z axis respectively. Hence, the plane meets x, y and z axis at a 0, 0, 0, b 0, 0, 0, c respectively. Let's visualize it. So a plane meets x, y and z axis at p, q and r respectively. Since here the meeting point is on the x-axis, only x value will be there, the other coordinates values will be 0. Here q is at y-axis, so y value will be there, the remaining x and z values will be 0. And in z-axis, the point r is marked, so only z value will be there, x and y coordinates will be 0. So the intercept form is x by a plus y by b plus z by c is equal to 1. X by a plus y by b plus z by c is equal to 1. Now the last one, plane passing through the intersection of two given planes. Equation of plane passing through the intersection of two given planes. It's quite simple one. Here two planes, pi 1 and pi 2 are the two planes, and pi 3 is the third plane which is passing through the intersection of pi 1 and pi 2. Let pi 1 and pi 2 be the two planes with equations r dot n is equal to d1 and r dot n2 is equal to d2. The equation of the plane passing through the intersection of the given planes is r dot n1 minus d1 plus lambda into r dot n2 minus d2 is equal to 0. So this one is quite simple equation if you really understand how to write. This is the equation of first plane, and lambda into this is the equation of the second plane. When you bring this one to the left side, r dot n1 minus d1 equal to 0. So first one, simply we can say that p1 plus lambda p2 equal to 0. That we can say, no problem. P1 in the sense equation of the first plane plus lambda into equation of the second plane equal to 0. This is called the vector equation, and Cartesian equation is a1x plus b1y plus c1z minus d1 plus lambda into a2x plus b2y plus c2z minus d2 is equal to 0. It's also similar to the previous one only. Cartesian equation of the first plane plus lambda into Cartesian equation of the second plane is equal to 0. This is the Cartesian form of equation of plane passing through the intersection of two given planes. Next, we shall discuss the condition for coplanarity of two lines. Two lines, vector r is equal to vector a1 plus lambda into vector b1 and vector r is equal to a2 plus lambda into vector b2 are coplanar if vector a2 minus vector a1 dot b1 vector b1 cross vector b2 is equal to 0. The condition is vector a2 minus vector a1 dot vector b1 cross vector b2 is equal to 0. This is the vector form, and the Cartesian form is determinant x2 minus x1, y2 minus y1, z2 minus z1, a1, b1, c1, a2, b2, c2 is equal to 0. Next, how to find out the distance of a point from a plane. The formula is modulus of vector a dot vector n minus d divided by modulus of vector n. The length of the perpendicular from the point P x1, y1, z1 to the plane ax plus by plus cz plus d is equal to 0 is modulus of ax1 plus by1 plus cz1 plus d divided by root of a square plus b square plus c square. This is a formula for finding the length of the perpendicular from a particular point to the plane ax plus by plus cz plus d is equal to 0. Next, we shall discuss distance between two parallel lines. First one is, it is a vector equation modulus of d1 minus d2 divided by modulus of n vector. Here r dot n is equal to d1 and r dot n is equal to d2 are the planes. This is a vector equation of the planes. Next one is the Cartesian form, that is modulus of d1 minus d2 divided by root of a square plus b square plus c square. Here the equation of the planes are in the form ax plus by plus cz plus d1 is equal to 0, ax plus by plus cz plus d2 is equal to 0 are the planes. Next, we shall bring the formulae for planes under one frame. First one we have learned, that is normal form. Vector equation is vector r dot unit vector n is equal to d, and the Cartesian equation is lx plus my plus nz is equal to d. Next one we have learned point normal form, that is vector form vector r minus vector a dot vector n is equal to 0. Cartesian form is a into x minus x1 plus b into y minus y1 plus c into z minus z1 is equal to 0. Next one, equation of a plane passing through three non-collinear points. The vector form is vector r minus vector a dot vector b minus vector a cross vector c minus vector a equal to 0. And the Cartesian form is determinant x minus x1, y minus y1, z minus z1, x2 minus x1, y2 minus y1, z2 minus z1, x3 minus x1, y3 minus y1, z3 minus z1 is equal to 0. Next is intercept form. Plane cutting off intercepts A, B and C from x, y and z axis is x by A plus y by B plus z by C is equal to 1. Next one is plane through intersection of two planes. That is vector r dot vector n minus d1 plus lambda into vector r dot vector n2 minus d2 is equal to 0. This is the vector form, and the Cartesian form is a1x plus b1y plus c1z minus d1 plus lambda into a2x plus b2y plus c2z minus d2 is equal to 0. Next, condition for two planes to be parallel. When it is in vector form, vector n1 cross vector n2 is equal to 0 vector, or vector n1 is equal to lambda into vector n2. If it is in Cartesian form, a1 by a2 is equal to b1 by b2 is equal to c1 by c2. Next one is condition for two planes to be perpendicular. In vector form, vector n1 dot vector n2 is equal to 0. In Cartesian form, a1 a2 plus b1 b2 plus c1 c2 is equal to 0. Next condition for a line and a plane to be parallel. Vector n1 dot vector n2 is equal to 0. And a1 a2 plus b1 b2 plus c1 c2 is equal to 0. This is for Cartesian form. And here these two conditions are same. Condition for two planes to be perpendicular and a condition for a line and a plane to be parallel. Both are same condition. Next one is condition for a line and a plane to be perpendicular. That is vector n1 cross vector n2 is equal to 0 vector, or vector n1 is equal to lambda into vector n2, or else a1 by a2 is equal to b1 by b2 is equal to c1 by c2. Here also condition for two planes to be parallel and a condition for a line and a plane to be perpendicular. Both are same conditions. Then next one, condition for two lines to be coplanar. The condition is vector a2 minus vector a1 dot vector b1 cross vector b2 is equal to 0. This is the vector form. And if it is in Cartesian form, determinant x2 minus x1, y2 minus y1, z2 minus z1, a1 b1 c1, a2 b2 c2 is equal to 0. Next, distance between a point and a plane. Vector form is modulus of vector a dot vector n minus d divided by modulus of vector n. And the Cartesian form is ax1 modulus of ax1 plus by1 plus cz1 plus d divided by root of a square plus b square plus c square. This formula also can be used to find the length of the perpendicular from a particular point to the plane. Dear students, today we have learned the basic concepts of plane and the equations of plane under different conditions. I request all the students to go through each and every point carefully, and after learning the equations of plane, please make a comparative study between the equations of line and the plane. While learning, if you have any doubt, please note it and keep. We will discuss it during the online session. Thank you for watching.